So any doubts from the test paper of the DPT, please let me know. I'll just share the paper so you can go through it. Okay, so I'll just take you through the questions and you can tell me whichever questions if anybody has a doubt. So this was the first question. Okay. I don't think anybody would have had a doubt in this question. And second one, okay. The third one, unfortunately, the question was not printed in full in the test, but this was the question. Actually, in your case, the question was printed in full, so no problem. Okay, so let's come to question 4. Most of you are asking about question 4. Okay, so just go through the question, then I'll explain. Okay, so this one is 100 grams, 200 grams, and you have to find the value of M1 so that the 100-gram block is at rest. Okay, Harpriya, I'll come back to the second question. So just be patient, everyone. Let me discuss the second question quickly, Harpriya, and understand. So see, in second question, what you can clearly understand from the free body diagram is the component of weight which is acting on this one is mg sine 53. So that is 4 by 5 mg and mg cos 53. Okay, whereas here the component of weight that is acting is mg sine 37. So that is 3 by 5 mg. And this is mg cos 37. Okay, and then of course there is tension, okay, and normal reactions. But clearly you can understand that which is the dominating force, because both have same mass. Okay, so the dominating force out of the two is this one. This force is dominating over this one, so this will tend to give the system an acceleration like this. And the component of this one's weight which is trying to drive the system in this sort of direction is dominating over the component of weight which is driving the system in that direction. Okay, so Harpriya, is that concept clear? That's how we can guess the direction. Okay, but the thing is, see, even if I assume the direction is wrong, okay, so let's try this question that way. My answer will tell me that it is wrong if I assume the direction is like this, and I solve the problem now. So then for the block A, I'll write the equation 3 by 5 mg minus T is equal to ma, and for the block B, I'll write the equation T minus 4 by 5 mg is equal to ma. So I'll get A as a negative quantity. I'll get A as minus G by 10 here. So the moment I get it, I know that the direction is opposite. It is opposite to assumption. So that means A is actually going up the inclined plane and B is coming down the inclined plane. This should be the correct direction. Okay. Right. Uh, so let's come to question 4. That is common doubt with a lot of people, and it was a bit of a tricky question. Okay. So I'm just going to work out this question fully for you. So 100 grams, 200 grams and M1, and the system is at rest. Okay, so let's switch to the whiteboard and solve it. Right, so question number 4. So we have a system which is like this. So we have to find the condition on M1 so that the 100-gram block is at rest. So condition on M1. Okay. So what you can do is you can just assume like this, that M1 is suppose going up at E, then the pulley is also coming down at E. Okay. And then with respect to the pulley, this one would be going up at E prime minus A, and this one would be coming down at E prime plus A. These are all the accelerations in the ground frame. It is all in inertial frame. So you have to find the condition that E1 should be 0. So that means E prime should be equal to A. This condition you have to find. So now you just make the FBTs of each one. So for M1, that is the 100-gram block, your equation is, now also if the tension in this string is T, the tension in this other string will become 2T. Remember, it's a massless pulley. Yeah. So the condition for this is that T minus 100 grams into G should be equal to M1 A1, which should be 0. So T minus 0.1 G is 0. So the tension you are getting is 0.1 G. And that's your first equation. Okay. Now for the second one, we're getting the condition that 200 grams into G minus T is equal to 200 grams into A prime plus A. Okay. Now see, already for this thing, for you had this condition. Okay. So actually, technically, this was your equation 1. There is a conditional statement here, so that is becoming your equation 1. So this is your equation 2. Okay. So this becomes 0.2 G minus T is equal to 0.2 into 2A, because you incorporate this now, that E prime is equal to A. And then you incorporate this also. So you have 0.2 G minus 0.1 G is equal to zero point 0.2 into 2A. So what does our A come out to be? 0.1 by 0.4. So G by 4. A comes out to be G by 4. Correct? And then you have the third equation for the block. Acha, this I have written as M1. So let's just write this as capital M1, so don't get confused. So this is capital M1. So the third equation is for capital M1. And for that, the equation will become 2T minus is equal to M1. Okay, so that's our, this one was our third equation actually. Okay. This one will become our fourth equation. So that's it. Now substitute everything. So 2 into 0.1 G minus M1 G is equal to M1 into A, which is G by 4. So 0.2 is equal to 1 plus 1 by 4 into M1. So M1 becomes 0.2 into 4 by 5, 0.8 by 5, or 0.16 kg. Okay, so in grams this will become, so that's 160 grams. So really I feel this is the easiest way of dealing with this question. Just solve it like a normal question you would have solved like this, but in that normal question put the condition that this one's acceleration in ground frame is becoming 0. So you'll get that additional constraint that a prime minus a should be 0. So a prime should be equal to a in magnitude. Understood? Now, a prime here is the acceleration of the system of 200 and 100 gram block in the pulleys frame. So if you look in the pulleys frame, the 100 gram block is going up at a prime and this one is coming down at a prime, the 200 gram one. So in the ground frame, what is happening? The net acceleration upwards is becoming a prime minus a, whereas this one's acceleration downwards is a prime plus a. Okay, people. So hope this is clear. Vineet, then Asmi, Shubham, etc. All of you. Jaini, clear with this question? Okay. So I think next question I have got in doubts from you people is the 6th question. Okay, so I'll just take you through the 6th question. So I'm switching to the test paper again now. Okay, don't worry, I'll share these solutions with you, so you don't need to take them down in detail. Just understand right now. Yeah, so 5th question, I don't think anybody will have difficulty. This will just have a combined acceleration downwards, this will have a combined acceleration upwards. I mean, that's pretty easy. 6th question, okay, well, don't think there should have been any confusion with this, but anyway, let's solve. It is probably a solving mistake if you're making some, if you're not getting the answer or something, it's probably a solving mistake on your part. See, if this has the tension T, that tension is acting everywhere like this, and naturally if this block is sliding down with A, this is moving with A. So first thing is you need to find out tension. Then only you can talk about the pulley's free body diagram, because you have to find the force exerted by the pulley on the clamp. So you need to make the pulley's free body diagram. So you need to find the tension. So for this block, let's say this is block B and this is block A. So for A, you have the equation T is equal to Ma. There's no friction anywhere. And for B, we have mg minus T is equal to Ma. So if you solve this system, you'll get A as g by 2, and that means tension is mg by 2. So once you got the tension, next thing now is you make the pulley's free body diagram. So understand that what is happening, the pulley is massless, of course. So pulley पे क्या क्या forces act कर रहे हैं? There is one horizontal tension acting like this and one vertical tension acting like this. So in fact, these two forces are at 90 degrees to each other, and they are trying to pull the clamp down like this. They are pulling the pulley against the clamp like this. So the clamp has to react by applying a reaction force like this. Okay. So ultimately, when you draw a proper vector diagram, the forces on the pulley are like this: tension, tension. This angle is 90, and the reaction force against it. So the net force is 0 on the pulley. So the reaction force has to be the vector sum of these two. So it has to be T root 2. So now you understand that on the clamp, the pulley is applying an equal and opposite downward reaction force. The pulley is pushing it with like this. So the clamp is pushing back with this. So this and this, they're an action reaction pair. So there you go. So once you understand that, now you can see that this reaction force is T root 2. So that is mg by 2 root 2. So that is mg by root 2. Okay. So that is the reaction force. Okay, people. So yeah, I'll show the 5th question, Tanish, don't worry. So 6th question, hope this is clear to all of you. So the pulley is massless, remember, because nothing is given about, yeah, it's given that it's massless. Now, even for example, if the question had not mentioned that the pulley is massless, you have to assume it's an ideal pulley. So it is frictionless and massless. Okay, people, so hope this is clear. Right, so I'm assuming you're clear about this. Okay. Yeah, so just show you the fifth question. Somebody asked just now. Yeah, this was the question, beta, Tanishq. Okay. So in this, you have to find the tension between in the string between B and C. So same way, now you just make the free body diagrams. Okay, solve the equation, then find that tension. Let's say the tension in the first string is T1 and the tension in the second string is T2, and the whole system has an acceleration E. So you get three equations and three variables. Okay, good. So sixth is done. Now let us move on to, anybody has a doubt in seventh question? I think a couple of people had a doubt in seventh. Yeah. So what I will just do is here, just magnify this a little so that it's easier for us to, okay, yeah. So see, in seventh question, what is happening is if your hand is pulling down the system, or that string rather, at a tension, at with a force F, then this string will develop a tension is equal to F. That's your first equation. Okay, so you can see that that tension is acting like this, like this, like this, like this, like this. Okay, and let us now label this pulley as P1 and this pulley as P2. Now that also means that this other string now will develop some tension, let's say T prime, and because the pulley is massless, so T prime will be equal to 2T. Now, because you see the free body diagram of pulley P1, so on pulley P1 it doesn't matter whether it's accelerating or not, the net force has to be zero because it's massless. Okay, so because this pulley's mass is zero, so net force on it has to be zero. Okay, so that is giving you this equation. So that's your second equation now. Okay, and now you look at the free body diagram of the block B with the pulley attached on it. And do this. Okay, so now you can see that on that the net force that is acting is T prime, which is 2T basically, plus T plus T. Okay, and of course there is the weight of the block. Okay, so the net force, if you want this one's acceleration to be zero, if you want this to be at rest, so 2T plus T prime must balance the weight of the block. Okay, so solving this system, basically what we will get is that 4F, because this is F plus 2F, should be equal to the weight of the block. This will be the solution to this part, you know. So weight of the block is given to us as 100 newtons. Okay, so that means the force has to be 25 newtons, because weight of this block given to us as 100 newtons. Okay. So that is the seventh question. And in the eighth, the force is increased. So now there's a net upward force. So you use the same free body diagram, but this time the upward force will dominate over the weight of the block. So it will be having an upward acceleration. Okay, so hope this question is clear to all of you people. Hitansh, today we are going to continue with Newton's laws, but we are going to look at more questions with wedge constraints and few more practice questions. Uh, Depending on time, we might take an introduction into friction or not. It depends. But in any case, like friction is not coming in your next test on 11th. So you have to prepare till the end of Newton's laws chapter. And of course, yeah, we'll discuss about spring forces. Very important. We'll discuss about spring force today. Yes. So let me just finish with this and we'll come to spring force. But again, it's not time taking. It's a very short thing. The understanding of springs. No, Manas, the topic for major test is Newton's laws. Friction is a different, is this chapter after that. Okay. So friction will not be there in this major test. Okay. Uh, Let me remove all this. Wait. Yeah. Yeah. Coming to that, ask me just a moment. Right. So seventh and eighth should be clear. In eighth, just change the value of F to 30 newtons. So the net upward force on that block will become 4 times this, so 120 newtons. So its weight being 100 newtons. Net force will be 4F minus weight, like that you can calculate. So that is mass into acceleration. Okay, ninth question. Huh? So ninth question, see what you have to understand is very simple. Just the free body diagram of this block. So free body diagram of this block में क्या क्या forces act कर रहे होंगे? Let's just see that. So here there will be a normal reaction force which will be along this direction on the block. It will be perpendicular to the plane of contact along this direction. This is the normal reaction, and this is what we want to find out actually, because the value of F is given to us in the question. F is given to us as 200 newtons, and actually nothing else is required. If you weight the hour, that is unnecessarily given to us. We don't require it because, but anyway, the complete free body diagram, there will be normal reaction, let's say N prime acting from the ground, and there will be the weight of the block which is acting through the center of mass, mg by this. So if you make a particle type of free body diagram of the block, you will see that the forces acting are this external force F, which is 200 newtons, this normal reaction N. Now iska direction you have to sort out. Okay, so you can see that this angle is 60, so this angle is 30. So you can see that this angle is 30, or this angle is 60, whatever. So you can see that here this angle will be 60 degrees. Okay, and apart from this, there are the other two forces, which is the normal reaction that the ground is applying N prime upwards, and the weight of the block mg downwards. Okay, so out of this, what all is known to us? This is known to us as 500 newtons, and this is known to us as 200 newtons. So we can find out the other two forces. Okay, in this case you've been asked only one of the two, but you can find out both. So you can see that N cos 60, oh sorry, this angle is 60, my mistake, just a moment. Okay, this angle will become 30. Okay, I'll tell you why this angle will become 30, because in this diagram, if you look carefully, this angle is 60, no, sorry, not that. So this angle is 60. Okay, so back here you can see that this angle is 30 degrees, no? Because this is the normal to it, so this should be 90. So here this normal reaction is acting at 30 degrees to the husband. So yeah, so coming back to this, N cos 30 will balance F. Now, this is along the x-axis, taking x and y like this. Okay, this is at rest, so net force should be 0. So that's it. This is all you need actually. Equation 1 is all we need, but we also have the equation that N prime along the y-axis, N prime plus N sine 30 is equal to mg. Okay. So this will tell us that our N is 400 by root 3, and this, if required, this would have told us that our N prime is 500 minus 200 by root 3 or something like this, whatever. Okay, but this is what we required. So that's why option C is the correct option. Work power energy will come later, Aditya. That will come few chapters down the line, because there's also circular motion after friction. Okay. But if you want, you can study work power energy. I mean, you can start reading about it and learning it on your own right now. Because once you're clear with constraint relations, calculus, and vectors, these things, no, you are prepared to study work power energy as a separate chapter. Basics of laws of motion and all that are clear. So you can start reading if you want. Better is if you do after friction, but still. Right, so this is clear, I hope. So after ninth, what is the next question you want to do? 10th, 11th, anybody? Okay, 16th. So we also have to discuss 14th. So anybody has a doubt before the 14th question? 11th, okay. So let's come to 11th next. Okay. 10th though is very simple. It's a HC Verma type of problem. So I'm sure. Okay, so we'll discuss 11th and 13th. Now see, 11th is again a bit of a tricky question in that sense. So in 11th, what is happening? I mean, it's conceptually little bit you have to understand here. So you have two men of masses 100 and 80 kg. Now the first one, now it doesn't matter what order they are in, okay, but I'm just assuming the 100 kg one is here and the 80 kg one is here. Okay. Now what is happening is the 100 kg guy is accelerating upwards, isn't it? Acceleration of, so he's climbing up with an acceleration of 2 meters per second square. Whereas this guy is climbing down with a uniform velocity. Okay, so that means his acceleration is 0 for this guy, but he has a downward velocity of 2 meters per second. Okay, so now what you do is, if this is, let's say, person A and this is person B, so you make the free body diagram of person A. Okay, so for the person A, what is happening is there is some upward force of tension. Okay, or you just think of this like a reaction force. Actually, you'll realize there's a frictional force because it's between his hands and the rope. The type of force is actually friction. Okay, but here you can just think of it like a contact force or whatever. So let's say this is F1 and his weight, which is 100 G, and under this action there is an acceleration A on him. Okay, so this F1 is the contact force, which is basically in the form of friction. Okay, between A's hands and the rope. Okay, he's gripping the rope, and that is providing friction. Okay. So that force. So basically, he's pulling down the rope, and the rope is pulling him up, like this. So anyway, so you will now get this F1 minus the weight of A is equal to mass of A into acceleration. So F1 will come out to be 100 G plus 100 A. Okay. So F1 comes out to be how much? If we take G as 9.8, so it comes out to be G plus A, that is so 100 into 11.8. So that is how much now? 1180 newtons. That is F1, just F1 alone. Okay, then you make the other guy's FBD, B's FBD. So on B similarly, there is some gripping force F2 and the weight of B, which is ATG. Okay, and acceleration is 0. So weight of B becomes equal to F2. So that becomes 80 into 9.8. So that is how much now? 98 into 8. So that is, okay, so this much of these many newtons. So this is F2. Now think of the rope. Okay, so if you think of the rope, what is happening is where A is present at that spot, A is pulling down the rope with a force F1, and where B is present, he is pulling down the rope with a force F2. Okay, so you'll realize that the tension in the rope, assuming the rope is massless, the tension in the rope in this region, let's say this is T1 or T2, okay, and the tension in the rope in this region, that is T. So T2 will be just F2. No, the portion of the rope that is below A but between A and B, that will have a tension of this much only. But the part of the rope above this guy, that will have a tension of T2 plus F1. So that tension will become F1 plus F2. So at the top of the rope over here, this tension is going to be how much? It's going to be F1 plus F2. So that is 180 plus 784. So whatever that value is, 16, 9. So 1964. So that should be your answer. Okay, so this is similar to those monkey type of problems also that we discussed from HC Verma. You have to be a little careful in these questions. Very easy, but just very conceptual. Yeah, how we got F2 again? Na? So free body diagram of block of the person B, Kevin. Okay, so he is coming down, he's sliding down, but with zero acceleration. No, he's coming down with constant velocity. So the net force on him has to be 0 because his acceleration is 0. Okay. So people, hope this is clear. Okay. Now I'm removing this, but unfortunately, if you want to see these solutions again, you'll have to go through the video. Okay, because this is not getting captured in the PDF which I'm going to send, or you try it again yourself based on what I'm explaining here, and if you have any difficulty, you can drop me a message later. Okay, so yeah, I think somebody had a doubt in question 12. Let's discuss about that. So 12 is about the direction of normal force. Okay, so what we have to understand is that whenever we have this kind of a situation, we have an inclined plane at an angle theta, then any type of object, the object could be any shape, doesn't really matter. But at the point of contact, kya hota hai? The plane of contact is the inclined plane. So the normal contact force is always going to be in this direction. It's going to be perpendicular to the incline. So same thing over here. यहाँ पे जो normal reaction है, let's say this is N1, this will be perpendicular to this. और यहाँ पे जो normal reaction है, this one will be perpendicular to this, like this. So coming back, so there is one contact point here and one contact point here. So you'll see that the normal reactions, so actually if you are used to doing this type of questions, you'll realize they are symmetric, so they will have same magnitude. But let me say that I have not guessed that yet. So suppose I have not made that guess, I'll assume that there are some different normal reactions, N1 and 2. Okay, Now again you will see that always this sort of a normal reaction will be along the direction which is perpendicular to this plane. So if this angle is theta, then this angle becomes theta, because this whole angle is 90. So this is 90 minus theta, so that becomes theta. So again coming back here, and of course the weight of the object is acting like this. So if you make a particle type of FBD, you can show that N1 is acting at an angle of 30 degrees to the vertical, and N2 is also acting at an angle of 30 degrees to the vertical, and Mg is acting vertically downwards. So whether you do resolution of forces or use Lami's theorem or whatever you do, you will find out that first of all, N1 is equal to N2. That you can see by balancing the horizontal components, and then you can see that N1 plus N2 cos 30 is equal to Mg. Okay. So now from this you will get that N1 is equal to N2 is equal to Mg by 2 cos 30. Okay, so that will become Mg by root 3. Okay, so 50 by root 3 should become the answer. Okay, so hope this is clear, people. Okay, right. So next, I think somebody had a doubt in question 13. Couple of you had a doubt in question 13. So let's come to that. Okay, so question 13 is again basically it's nothing but a sort of monster problem for constraint relation. And as I've told you, whenever we have this kind of monster problem, you should always prefer the virtual work method or the virtual power method. Don't go for the thread length conservation, because here you'll have to write the equation to conserve 3 thread lengths. That is going to get quite crazy. Okay, so you don't want to do that. Okay, so go with the virtual work method. Okay, so start with this. If the tension in this string is T, then it's acting like this. Okay, now this pulley P1 is a massless pulley. Okay, so that will immediately show you that the tension in this string, let's say T prime, will be 2 times T. That's your first equation. So now T prime is acting like this. Okay, whereas this point there was T. Okay, and now again this pulley P2 is also massless. Okay, so if the tension in this string is, let's say, T double prime, okay, then you have T double prime is equal to 2 times T prime. So that's this equation, or T double prime is becoming 4 times T from these two equations. Okay, so now you look at the free body diagram of block B. So the net tension acting on it is T double prime plus T prime plus T, which is 7T. Okay, and it is given to us that B is moving upward, suppose. Okay, at acceleration a1 or whatever, a2, or velocity v2, and A on the other hand is coming down with a velocity v1, acceleration a1, etc. But on A, the tension acting is only T. So forget about the other forces. Okay, just the net work done by tension in the system should be zero, or net power delivered by tension in the system should be zero. So on the pulleys, you can anyway say tension is delivering net power zero, because the net force due to tension is zero. You don't only worry about block B and A. So on B, tension of 70 is delivering a positive power because this is happening. On A, it is delivering a negative power because it's opposite in direction. So, so V1 is equal to 7 V2. So E1 is equal to 7 A2. Okay. So this is the constraint relation. So in this question, you only had to solve the constraint relation. Then you didn't have to make FBD equations and all, because one acceleration was given to you. You had to just find the other acceleration. Yeah, I think we discussed a similar question in class, exact same arrangement, but there had given the masses of the blocks and you have to find the accelerations. Was the only difference. I mean, these questions will be of this type only. Either there'll be two pulleys or three pulleys, or so if there's three, then the ratio is 7:1. If it's two, then the ratio is 3:1, like that. So the questions can't be too different from each other. Okay. All right. Let's next we are moving on to 16th question. I think a couple of people requested 16th question. This though was directly from HC Verma, if you recognize this question. So you have to just make T1, T2 accelerations and all that, and eliminate T1, T2. 14th. Okay. Okay. All right. So let's discuss 14th. So in 14th, you can see that this one is quite heavy na, compared to these other two. So its weight will dominate. Okay. And as a result of that, this has a downward acceleration A, this has up the inclined plane, this has vertically upwards. And then take the tension in this string as T1 and take the tension in this string as T2. Okay. So let's say these blocks are A, B, and C. So for the block A, we'll have the equation 0.5 G, that is the weight of the block, minus T2 is equal to 0.5 A. That's our first equation. Then for the block B, now for the block B, you'll have to understand that there is also components of weight. So there is also mg sine theta and mg cos theta. And apart from that, there's normal reaction. And then there are these two tensions, T2 and T1. All these forces are there. So for block B, the equation will become T2 minus 0.1 G sine 30, that component of weight. Okay. And again, there's also T1 pulling it down. So minus T1 is equal to 0.1 E. That's your second equation. Okay. And for the block C, it's very simple. The T1 is greater than its weight, which is 0.05 G. And this is giving it an acceleration of E. Now solving this is very simple. You just have to eliminate T1 and T2. So add the equations. Add all three equations. So T2, T2, T1, T1 gets cancelled. So you get 0.5 G minus this term will become 0.05 G, because sine theta is 1 by 3, minus this one, which is 0.05 G again, will become on the other side 0.5 plus 0.1 plus 0.05 E. So that's it. From this you will get your E as 0.5 minus 0.1, so that is zero point 0.4 divided by 5 plus 1 6 plus, so 0.65 G. Okay, so 4G by 65, so that is something I've done wrong in calculation, is it? Just a minute. What is the calculation mistake I made here? Oh, okay, okay. It should be 40. My mistake. Correct. Correct. So then it will come out to be 8 by 13. Correct. All right. So hope this is clear. So let's move on to 16th now. I don't think anybody had a doubt in 15th question. So in this we have to find the condition for this to lose contact. Okay. So condition to lose contact will basically mean the normal reaction should become zero between them. So what you do is you assume that they've lost contact. If there's lost contact, then on this block there is only this force because normal reaction is zero. Normal reaction ground is applying, but that's a different matter. So this will have an acceleration of F by capital M. That's the first thing. Okay. Now the second one, what you do is, this was an inertial frame, of course. Okay. Now the second one, you make it in the non-inertial frame of the wedge. Okay. So your non-inertial frame is moving with an acceleration E like this. Oh, sorry, with an acceleration E in the opposite direction, negative X direction. So now on this block, there is first of all a pseudo force like this. Okay. And then of course it has its weight mg like this. And then the thing is that the normal contact force is supposed to be zero. So there's supposed to be no normal contact force. Okay. So the condition for the normal contact force to be zero is that, as you can see, the sign component of pseudo force should automatically balance the cos component of weight. This is the condition. Okay. This is the condition for normal reaction to be zero. Okay. So as you can see, E should be equal to G cot theta. So that's your second equation. So now put it back in the first equation and you'll get the condition on F. Substitute this here. So you get F is equal to mg cot theta. Good. So anything else, anybody? Or the remaining questions are clear? This was simple again, HC Verma type of problem, constraint relation and free body diagram. I think everything was simple. This was also same thing, constraint relation, free body diagram. Okay, this one was based on what we discussed last time. Okay, question 20. Okay, let me check it out. Question 20 now is again that type of question. Okay, so masses of M1 and M2 are given to us. Let's look at this carefully. So okay, so M1 is 2 kg, M2 is 5 kg, G we have to take as 9.8. Okay, so the value of force so that M2 will stay at rest. Okay, so now see, that's pretty simple. You don't have to worry about much here. The pulley is massless pulley. So you make a free body diagram of the pulley, and you see whatever force you are applying on the axle, that will result in net force 0. The tension developed. Okay, so because this is massless, okay, so net force should be 0. So the tension is F by 2. Okay, now you come to M2's free body diagram. Okay, so on this you can see that there is tension, there is weight, and there is normal reaction. Okay, so for it to remain in contact, if M2 remains in contact with the ground, N should be greater than 0. Okay, so that means M2G should be greater than T. So T should be less than, what is the weight now? 5 into 9.8. Okay, so that's it. Now combine the two. So you can see that for N to be greater than, it can just about be equal to also, just as it loses contact. So that's like the limiting condition. F has to be less than equal to 10 into 9.8. Okay, because F is equal to 2T. That is the condition. Yeah, the answer key I'll share, but answer key is available on the website also, no? Don't worry. Answer key will be available on the website too. Okay. All right, people. So hope all this is clear. Okay. So now let's go back to the couple of things remaining in the theory portion, and then we will come back to any further questions and doubts and things. Okay. So the next thing we'll discuss is the concept of spring force. Okay. So actually, we'll discuss the whole idea of springs and something called Hooke's law, which tells us about the type of force that a spring applies. Answer key Ayush will be available on your this thing, on your login on the website when you go to your tests. Okay, matlab you go to my tests and previous tests taken. Acha, result is not reflecting yet. It will reflect soon. Okay, but in any case, like if you need the answers of any questions, just let me know. I'll help you out with that. Okay. or I'll just send you the answer key. I'll send you the answer key on the group. Don't worry. Okay. I'll send you if you haven't got it. Okay. So now let's understand the behavior of an ideal spring. Okay. First of all, it is massless. Okay. Or in other words, the mass of the spring should be negligible. Okay. It should be negligible compared to the mass of any other objects attached to it in the system. Okay. So first of all, that's, and second thing, an ideal spring obeys Hooke's law. Now, Hooke's law is something very simple. It tells that the restorative force, I'll explain what restorative force is directly proportional, okay, to the amount of deformation. So I'll explain what these two terms mean. Okay. So basically what happens is that, okay, whenever a spring is deformed, by deformed we mean either it is compressed or extended. So either in a state of compression or in a state of extension, it develops an internal force, like a tension basically, which opposes the deformation. Okay. In other words, it tries to restore, okay, the spring to its natural length. So that force is called the restorative force. And by deformation, we have seen it is either the amount of extension or the compression. Okay. So basically, in simple language, we say that this statement is like this: that the spring force is minus kx, where x is the compression or the extension in the spring. Okay. So just make a quick note of this and you will understand. Or actually, wait, before you make a note, let me explain this with a diagram. Okay. I'll come back to this statement. So let me explain this thing with a diagram. Then it'll be clear to you what is the meaning of deformation and all this. So let us say this is a spring when we are not applying any forces to it. So this is what we call the natural length of the spring. So you can call it the, okay, undeformed state. Okay, natural length state or the undeformed. It's not deformed in any way. Okay. Now from this state, for example, if we want to extend the spring, if you want the spring to go into this kind of a state, okay, such that its length has now become L plus X. Okay, so for that we'll have to apply some external force from both sides. So the moment we apply that external force, the spring develops an internal tension. Okay, so that internal tension is what we call the spring force. It is the restorative force developed within the spring. Okay, and this is developed due to something called elasticity. Okay, so elasticity is again something we'll discuss as a material property in a later chapter, but you understand that all materials are elastic. Okay, some are very elastic like rubber, etc. Some are not so elastic, but all materials have an inherent amount of elasticity. That is, when you stretch them, they have a tendency to come back to their natural length. When you compress them, they have a tendency to push back through their natural length. So that is the inherent material property, which is called elasticity. Okay, this is the restorative force developed within the spring due to the elasticity. Okay, so here you can see that in this diagram, the spring is in an extended state or a deformed state, but the deformed state is in the form of an extension. Okay, so x is the extension, whereas here the spring was in natural state. Okay, now as opposed to this, we might also take the spring into a position where instead of this it gets compressed. Okay, but to compress it we will have to apply external force like this, so that the state of the spring has gone from its natural state to a compression. So if it is compressed by x, then again it is a property of the spring that it will develop its internal tension or internal force. Again, that is the restorative force. Okay, and here x is the amount of, so in this diagram the spring is in compressed state, so x is the compression of the spring. Okay. Okay, so according to Hooke's law, whether we are looking at this situation here or that situation there, this spring force will have a magnitude of some constant into x, but with direction we can say it will become minus kx because it opposes the extension. Same over here, the spring force will have a magnitude of kx, but if we write as a one dimensional equation it is minus kx because it will oppose the change. So the constant k over here, we'll discuss about it. That's a property of the spring which is called the spring constant. Okay, but first of all, the meaning of Hooke's law. This is the meaning of Hooke's law. Yeah, external force will have to balance the restoring force. That will also come up from the fact that the spring is massless. But before we get into all that, just to understand how much is the restorative force, how much restorative force is the spring going to develop. So the answer to that is it's going to develop a restoring force according to two things. One is the property of the spring, that is whether it's a very stiff spring or it's a comparatively less stiff spring. So that is the property which is called the spring constant, which is denoted by k. And the other thing is that the amount of restorative force is actually proportionate to how much deformation we are giving. So if we are compressing the spring and gradually we are compressing it more and more, so gradually the restorative force will increase in proportion to the amount of compression we are giving. Same for the extension. So we'll discuss a little bit more about the constant k over here. Right now you just understand that in this equation k is a constant. So what that constant is we'll discuss. Okay. Yes, the coiling also generates Ayush, that's correct. But among other things, I mean, it's not just the way the spring is coiled, but also the material of the spring. So I'm coming to the concept of spring constant. So Hooke's law, the restorative force applied by the spring, this is a 1D equation. So instead of writing it as, this is minus of kx I cap. Instead of writing it like this, we are writing it like this here. Okay, where I cap is along the axis of the spring. Instead of that, we are writing it like this. So in this, k is a constant, okay, which is a physical property of the particular spring we are talking about involved. Okay, and therefore it is called spring constant. It's the spring constant of that particular spring, or sometimes we also call it the stiffness of the spring. Okay, and k is measured in newtons per meter. Okay, but a more common unit is newtons per centimeter, which is a hybrid unit. It is neither CGS nor SI. So k actually depends on a number of things. The spring constant k itself depends on various factors, like the material of the spring. Okay, steel spring or copper. Okay, or anything, whichever metal it is made of. Then the thickness of the wire used to construct the spring. Okay. Then the coil density. You're coiling the spring like this. So the number of coils per unit length, that is the coil density. Okay. Then total length. Okay. Radius of the coil. So all these things. So this is actually more about the sort of experimental aspect of springs. Okay, there is no direct formula at this stage between the spring constant and all these factors. It comes more as what is called an empirical law. That is, it comes from experiment. It determines beta. I mean, we'll see that the spring constant is actually inversely proportional to the total length. So we'll understand a little bit more about that in a chapter called elasticity. Elasticity and something called Young's modulus of elasticity which will come in the chapter called properties of matter. So when we come to that chapter, we'll understand a little bit more about this. Okay, now currently the job for us is that assuming we know the spring constant or we know the behavior of the spring, how we apply Newton's laws to it. So let's understand an example of that over here. Okay. So here, given that A and B are identical springs, okay, of spring constant equal to 50 newtons per centimeter each, okay, and natural length 100 centimeters each, okay. G is equal to 10 meters per second square. Now it is observed that the spring A has an extension of 1.2 centimeters. Okay. That means this length, let's say L prime, is 101.2 centimeters. So from this we want to find M and the tensions in each spring, okay, and the extension in spring B. Just try this out. So this is in a vertical situation. Acceleration due to gravity is acting like this. So you've taken two ideal springs and okay, Amok, I'll show you that later. Okay, I'll come back to that last line. Just try this question out first. Okay, okay, thanks so much. Yes, that's correct. Kevin, your answers are correct. Okay, so what you can see that in the spring A, from this information you can see that the tension in the spring A is going to be K into X of A. Okay, so that is going to be 50 newtons per centimeter multiplied with 1.2 centimeters. So that is 60 newtons. That is the tension in spring A. Okay, whereas the tension in spring B is going to be K into XB, which we don't know. Okay, but coming back in the free body diagram, you can see that this is the tension in the spring A. Okay, the spring is extended now, so it will apply an inward force, and this is the tension in the spring B. Okay, so you can see that tension in the spring B is the weight of this block, and tension in the spring A is the weight of this block plus B. So combining these two equations, you can see that the tension in the spring A is 3 mg. Okay, and this we already know. Okay, now from this you can also see that, so connecting this and this, now you can see that the tension in the spring A, which is 3 mg, is equal to 60 newtons. Okay, so that means M is equal to 2 kg, because we are taking G as 10. Okay, and that also means that the tension in the spring B is 2 mg, so that will become 40 newtons. So therefore K into XB will be equal to 40. Now K was 50 newtons per centimeter, into X will become 40 newtons. So X will be 4 by 5 centimeters, or XB will be 0.8 centimeters. So this becomes the solution. Okay. So I will just make this FBDs also to just show you. So on this there is tension in A, tension in B, and its weight, and it's at rest. And on this there is tension in B, and this one's weight, which is 2 mg, and this is also at rest. So that is how we are getting these equations, equation 1 and 2. Okay, so people, hope all the steps are clear. So actually, that's all there is to springs. I mean, in terms of application in Newton's laws, springs have more application in chapters like work energy theorem, etc. So we'll be seeing them throughout. But this is your first sort of exposure to spring force concept. Okay. So now you can also understand that both the springs are in extended state right now. This L prime is actually natural length plus XA. So it's at 100 plus 1.2 centimeters. Whereas similarly, if this length is now some L double prime, this is also at natural length plus some extension. And as it turns out, that extension for B now is zero point 0.8 centimeters. So the extension for B is zero point 0.8 centimeters. The extension for A was 1.2 centimeters. And because they are extended, that's why the internal force applied by the spring is inwards, like this. Okay, so hope this question is fully clear, people. Fine. Now let's pick up another question based on this. So next example, what is happening is we have this kind of a situation. There's like a thin platform, and on top of that we have a block sitting. And this is, so this platform has a mass m1 of, let us say, 10 kilograms, and this block has a mass m2 of, let us say, 15 kg, and this is a spring which has a spring constant of 100 newton per centimeter. Okay, so and g is 10 meters per second square. So the system is initially in equilibrium. Okay, so first thing is find the compression x of the spring. Okay, now the second part is more interesting. Second part is, now the block is suddenly removed by some external agent. Okay, so find the acceleration of the platform at the instant, that means just at that moment, just after the block is removed. So you'll realize instinctively that the moment you remove the block, because that weight is gone, the platform will tend to jump upwards. So it has some instantaneous upward acceleration at the moment when you just remove the block. It jerks up, So you have to find that acceleration. Yeah, I mean, you can do that. You can convert spring constant from Newton per centimeter to Newton per meter, though it's not necessary because you can give the answer in centimeters also. So for the conversion, you should note that 1 Newton per centimeter is 1 Newton divided by 1 centimeter. So it is 1 Newton divided by 10 raised power minus 2 meters. So it is 10 raised power 2 newtons per meter. So 1 Newton per centimeter, if you ever want to convert it, is 100 newtons per centimeter. That is a conversion factor. Yes, very good, Kevin. That's correct. Yes, 2.5 centimeters is the correct answer for the compression of the spring. What about the acceleration? So for the first part, you have to understand very simply that it's just about free body diagram. Is block pay, the platform is applying some normal reaction from below, let's say N1, and it has its weight, which is 15G, and it's at rest. Okay, this is the state of the block. So you have N1 is equal to 15G is equal to 150 newtons. Okay. Now you come to the free body diagram of the platform. So and on the platform now the block is applying a downward normal reaction. Okay. The platform has its own weight, just 10G, and the spring is applying an upward force, spring force, or tension in the spring. So the spring is in a compressed state. The spring is in a state where it's compressed like this. It is at L minus X kind of state. So that's why it applies tension or spring force like this on either of its ends. Okay. So from that you can see that for this we have the equation that Kx balances N1 plus M1G. Okay. So equation 1, equation 2. So from that you can see that Kx is equal to 25G or 250 newtons. So X will become 250 newtons divided by 100 newtons per centimeter. So X will be 2.5 centimeters. So this is the first part of the question. Yes, Ashmi, that's correct. Pritin, your answer is correct, but units you people have to be careful. Your units are not correct. You will get the acceleration in meters per second square. Both Naman and Pritin, Varun also. Okay. So you can see while this is X centimeters, no, but the spring force Kx, that is how much? That is 250 newtons. It's not millinewtons or something. So you have to keep this in mind. This is what will going to come handy in the next part of the question. Okay. So anyway, now coming to the second part. So the second part, the important thing you have to understand is not that at the moment when we just remove the block, the spring has not got a chance to change its state. So the spring is still applying an upward force of 250 newtons. But that normal force, that normal contact force N1 suddenly disappears when that block is removed. So that is not there anymore. So you just have this and the weight of the block, which is 15G. So this is more than this. So that is 150 newtons. So the block jumps up with an acceleration E. I mean, the platform jumps up with an acceleration e. Okay, so kx minus m1g is equal to m1e. So substituting this, you will get the acceleration. In fact, is very large. You will get it as 15 meters per second square. Sorry, this is 10g. My mistake. So this will be 100 newtons. Okay, so that's why this is becoming 250 minus 100. So it has an acceleration of even more than g, because the pushing force from above was more than its weight. No? So when that is suddenly released, okay, people. So hope this is clear. Okay, so that is more or less about spring force type of questions. Now you can complete the few questions remaining in HC Verma about spring force. Now we'll discuss a few more things in due course also. Okay, but next I want to do an example of wedge constraint. Wedge constraint applications. So for that, we have a system like this. Let's say like two identical triangular wedges on a smooth surface, and then what we have is a thin rod, but the rod is shaped such that the ends of the rod are not, they have a slight curvature like this. So this is a rod of mass small m and length l. Okay, so given that capital M is equal to 5 times small m and theta is equal to 53 degrees, all surfaces are smooth, the system is released from rest. So find the accelerations of the rod and the two wedges. Take g as 10 meters per second square. So just try this out. So that rod has that kind of a shape, that the end of the rod is like this, rather than like this. It's been cut like this so that it fits exactly into that situation. Okay, so just continue working on it. I'm just making the free body diagrams. So on each of the triangular wedges, you see that the vector forces you have will be like normal reaction like this, symmetrically same normal reaction like this. So if this angle is theta, this one will be at theta to the vertical. And of course, weights and some kind of normal reaction from the ground. So as a result of this has an acceleration A like this will have same acceleration A1 like this. So you can see that capital N sine theta, that this angle, is equal to capital M A1. This is our first equation. Okay. Okay, Aditya, I'll just verify your answer. Okay. Now on the rod, the forces which are acting on the rod will become like this. N and N, small mg downwards, and it's having some acceleration A2 downwards. Okay. So for the rod, you can see that so if you represent the rod as a particle, there are two symmetric normal reactions acting like this, which are at theta to the vertical, and weight acting like this, and it's coming down with an acceleration A2. So the equation becomes mg minus 2n cos theta is equal to m A2. That's your second equation. Okay. And now we need a constraint relation. So for the constraint relation, you can see that what is happening is that at this point, the normal reaction is acting in this sort of direction, and this point is moving with some velocity, let's say v1 in this sort of direction. Okay. And same for the other one. So same thing, normal reaction v1 in this, but as far as the rod is concerned, so on the rod you can see normal reaction is acting in this sort of direction and this sort of direction, whereas the point of application where the normal reaction is acting is having a downward velocity v2. So when you apply the virtual power method, you can see that, just magnify this a little. So you can see here that this angle will be 37 degrees, because with the vertical this was 53. This angle will be 37 degrees, whereas here this angle will be 53, this angle will be 53. So when we apply the concept that net power due to normal contact force should be 0, we'll get for these two there will be 2n v1 cos 37, and for these two there will be sorry, the angle with the vertical is 53, my mistake. Because theta was 53 degrees. Okay, so we will get 4 by 5 v1 minus 3 by 5 v2 is equal to 0. So v1 is 3/4 of v2. So a1 is 3/4 of a2. So this will become our constraint relation. And that is your system of equations, which now has to be solved. So this is our complete system of equations. Okay. So this is telling us that 4 by 5n is equal to capital M, which was 5 times small m into a1. That is what we had. This is telling us that mg minus 6 by 5n is equal to ma2. Okay, so we can substitute a2 as 4 by 3 a1. So we have mg minus 6 by 5n is equal to 4 by 3 ma1, and the above equation is, from this we can substitute n as 25 by 4 ma1. We can substitute this also here. So mg minus 6 by 5 into 25 by 4 ma1 is 4 by 3 ma1. So g is equal to 15 by 2 plus 4 by 3 a1. So g is equal to 45 plus 8, so that is 53 by 6 a1. So a1 is 6g by 53, and therefore a2 is 4 by 3 of this, so 8g by 53. So these are the values you should be getting. Okay, good. Okay, so the important thing is the 3 equations, and out of that also the most important is the constraint relation. This virtual power method and the constraint relation, this is extremely important. Okay people, so this was just an additional question for practice. So now really look to complete all the problems from booklet and HC Verma over the next week and a half for Newton's laws of motion. Okay, in booklet, just look for questions which don't have friction, because the exercises are mixed. So just try to work out all the questions where there's no friction involved. Okay, and that's it for today's session then. All the best.